Welcome to our discussion on the state of the art in embedded development. The landscape has really transformed in 2025. We're talking about AI-assisted coding, edge AI, RISC-V going mainstream, and even a strong push for memory-safe languages coupled with DevSecOps practices.
Absolutely, it's like a complete overhaul of how we build our devices. Where do you want to start?
Let's kick off with the role of AI in embedded development. The idea is that AI is not just a component in our end products, but actually in the tools we use to create them. We're seeing AI-generated code that can draft firmware routines and even debug on its own. It's like having an assistant that handles the boring parts so engineers can focus on design and high-level problem solving.
Yep, that's a massive productivity boost. But isn't there a worry about maintaining rigorous quality control when code is auto-generated?
That's a great point. Teams are already putting in safeguards. They require human oversight, review, and even use traditional static analysis on the AI-created code to ensure it meets strict quality and safety standards. So it's more like the developer becomes more of a system architect or code reviewer rather than typing every line.
So the AI is like a co-pilot, making sure routine stuff is taken care of, while human expertise remains in the driver's seat.
Exactly. And that extends into on-device intelligence too. Edge AI is booming. Embedded devices are now running machine learning models locally. Think about autonomous vehicles that make split-second decisions, or smart home devices that process voice recognition without cloud support. It's revolutionizing latency and privacy concerns.
On that note, these edge AI models, they can run on microcontrollers with barely any memory, right? How are developers achieving this?
Right. They're using frameworks like TensorFlow Lite Micro and TinyML libraries. Under tight constraints of memory and CPU, even a Cortex-M or a RISC-V microcontroller can do keyword spotting or anomaly detection. It's a step change from classic approaches in embedded coding.
I mean, that's really pushing the envelope. Now, switching gears, let's talk about RISC-V. It's been such a transformative force.
Oh, definitely. RISC-V has come a long way from being an academic curiosity to a mainstream foundation. With over 10 billion cores shipped by 2023, it's now a staple in microcontrollers, IoT devices, and even auxiliary cores in larger systems.
Exactly.
Its open source nature means no royalties and a more flexible platform for innovation.
I love that part. The openness. It really democratizes design choices. But I have a small challenge here. Do you think the cost savings and openness outweigh the potential complexities of a new memory model, especially when compared to something tried and true like ARM?
That's a valid challenge. While the RISC-V memory model and interrupt architecture might be new territory, the robust toolchain support from GCC and LLVM, along with active community support, helps smooth that transition. Plus, the flexibility allows custom instructions tailored for specific workloads, often translating into more efficient chips overall. So the long-term benefits seem to justify the learning curve.
It also sounds like major industry players like NVIDIA and Google are backing RISC-V, which signifies its staying power.
Absolutely. With government investments and billions of cores being integrated, especially in consumer devices and even GPUs, RISC-V is making vendor lock-in a thing of the past.
Moving on, another major trend is the open source software dominance in embedded systems. This is huge. It's no longer a niche or fringe option. It's become the backbone of development.
Right. Open source has fundamentally altered our approach to firmware and OS design. Now, whether it's Linux, Zephyr, or FreeRTOS, almost every new project starts with an open source platform. It's a drastic shift from the days of vendor-supplied proprietary kernels. Developers get unparalleled flexibility and community support, and it levels the playing field for startups versus established firms.
And when it comes to security, more eyes on the source means risks can be spotted and fixed much faster, right?
Exactly. Open source and security are like best buddies here. It not only speeds up innovation, but also makes embedded devices more resilient. Even in safety-critical systems, we're seeing open source projects push for certifications that were once only available with proprietary systems.
I find it fascinating that now even development boards like Arduino are integrating RISC-V and leveraging open source ecosystems. It really makes innovation accessible to hobbyists too.
Right on. And speaking of accessibility, modern programming languages are undergoing a transformation too. There's a shift from legacy C to memory-safe languages like Rust, modern C++, and even higher level ones like Python for non-critical tasks.
Yeah, it's the evolution from we only knew C to a broader language palette that emphasizes safety and productivity.
It's like moving from an open field to a well-fenced garden. With languages like Rust, the compiler's ownership model prevents whole classes of bugs like buffer overflows. And modern C++ 17 or C++ 20 brings in smart pointers and const_XPR, making the code less error-prone. Now you get high performance with improved safety.
But are there any cases where legacy C would still be preferable? I mean, sometimes the bare metal control is important, right?
Sure, C and assembly still hold an edge in terms of raw resource efficiency. But modern hardware has come a long way. Microcontrollers nowadays have more RAM and processing power, which means languages like Rust can perform on par with C, often with much better reliability. So the trade-offs are becoming less critical.
Right. And even MicroPython is making a mark for tasks like prototyping and educational projects, especially when development speed is more important than ultimate performance.
Definitely. That hybrid approach, using a low-level language for real-time drivers and Python for higher-level logic, is really shaping development workflows. Azurio's Canvas software suite, for instance, uses this mix perfectly, pairing C for hardware drivers with Python for application orchestration.
That's a great segue into our last major topic, DevSecOps and CI/CD with hardware-in-the-loop testing.
Right? And this is where the traditional, somewhat manual world of firmware development meets modern automation practices. Instead of manually flashing devices and running tests on someone's desk, companies now integrate automated CI systems that build firmware with every commit. They use CI servers combined with hardware setups that flash and test code on real boards, catching issues early.
It's a game changer for catching those elusive bugs that only surface when interacting with real hardware.
Yes, and that's where hardware-in-the-loop testing comes in. Imagine rows of test racks where Raspberry Pis trigger robot framework scripts to flash firmware and run a battery of tests on each device. This automation ensures that even hardware interactions like timing or interrupt sequencing are validated continuously. It's like your firmware is going through a rigorous boot camp before it ever makes it to production.
And it's not just about testing once, it's a shift-left approach, catching integration issues early. Plus, security is built into the process by evaluating vulnerabilities at the time of code commit.
Right. Moving security evaluation upstream is a smart move. It ensures that as devices become more connected, they aren't leaving openings for potential breaches. The combination of automated testing, continuous integration, and security checks means that firmware updates become routine, predictable, and much more reliable.
I mean, it's almost like updating your smartphone. Seamless, continuous, and with hardly any disruption. And when you think back to how manual everything was not too long ago, it's a remarkable evolution.
Absolutely. Integrating all these trends creates a virtuous cycle. Better tools enable faster development, which in turn allows for more experimentation and innovation in embedded systems. And with each innovation, be it AI-infused development, RISC-V's open flexibility, open source dominance, memory-safe programming, or rigorous DevSecOps, The hardware we build becomes smarter, safer, and more efficient.
It's truly a new era. The embedded systems of 2025 aren't just an afterthought on a chip. They're critical, intelligent components that drive modern applications, from IoT to medical devices to autonomous transport.
Yeah, and the convergence of these trends reinforces the benefits of each. For example, the safety guarantees of Rust complement the rigor of continuous integration testing. Similarly, RISC-V's open architecture pairs perfectly with community-driven open source tools.
Right?
This integrated approach is what's really pushing the field forward.
I love that perspective. It's not just about individual trends, but how they interlock to create a more efficient and innovative development ecosystem.
Exactly. If you think back just a decade ago, our approaches were so rigid and siloed. Today, it's this fluid, collaborative, and iterative process where AI, open systems, and modern languages help engineers build reliable, secure devices much faster.
It's so dynamic. And with the rate at which technology is evolving, I can only imagine that even more disruptive trends will surface.
True. For instance, future edge devices might even incorporate neural networks that learn on-device and continuously improve. Or we might see a further rise in customized silicon designed around RISC-V, optimized entirely by open-source collaborations. It's an exciting time for embedded engineers.
Indeed. And for anyone in the industry, staying updated with these trends isn't just beneficial, it's essential to remain competitive.
Right. Embracing these trends is like having a roadmap to the future of embedded systems. Engineers who learn to harness AI tools, adapt to RISC-V, contribute to and use open source software, and master new programming languages will be the pioneers of tomorrow.
Before we wrap up, let me ask one last thing. Do you see any pitfalls with this rapid transformation? It almost seems too good to be true.
Well, every transformative shift comes with challenges. You've got learning curves, investment in new infrastructure, and the need for continuous integration between diverse technologies. But the industry is resilient. By embracing a culture of collaboration and continuous learning, we can address these hurdles. It's like, evolving together as a community.
Right?
And that collaboration is what's turning these challenges into opportunities.